Okay, that's the recording started. All right, so this week we are following the materials as usual. You will remember that in the module materials, you know, the same place where you can get the links to the workshop and the syllabus so that you can keep up with when everything's happening. He hinted. Now we're just following through in the chapters. Last time we were on process scheduling. We're then going to skip 2 chapters, so we're not doing process synchronization or appropriately deadlocks. We're going to jump to memory management. Okay, I've left the stuff in there if you want to look at it, and it's definitely worth having a look at, but there's only so much that we can do in a second year course. So we are going to jump to main memory and memory management. So that's what we're going to talk about today. And of course, now that you've all come on during the test and confirmed your name with your picture, I know that you all have cameras and microphones, so I'll be expecting you to jump in a lot more often and not just sit back and be entertained. Genuinely, I'm havering on because, again, my computer's just stopped. It won't even start this PowerPoint slide. Wow. That whole silence, plus all the talking beforehand, was how long it took for me pressing start the slideshow to that appearing. It's going to be a long day. Buckle in. You know, like you would on a Disney ride. But that wasn't the reason. Okay, we want to talk about memory management. Absolutely, I'll take money. Part of the reason I did actually get a new laptop, which of course the absolutely excellent, there we go, fancy thing thinks is background, so I can make it disappear. That's good. I've got a new laptop. Problem is, it's only got one connection, so I can't run multiple screens, and it's also not got a touch screen, so I can't do my stuff where I write on the screen, and sometimes that's really helpful. So I'm sticking with the old one, which normally is okay. I'm guessing it's doing an update in the background, as is usual. I have told it not to do those unless it's between 8 at night and 6 in the morning, but it just doesn't listen to me. However, my GoFundMe page will be available very shortly. I'm accepting donations for, you know, one of those big curved screen monitors. That would do me. That'll be fine. Then if I've only got one, I can still have different screens. All right, so let's talk about memory management. And of course, one of the things that we'll be doing as usual is talking about multiple ways that we can approach memory management. All of which are used in different operating systems, none of which is the right answer. And I don't know how many times I've said that now, but it's to give us an idea of ways of approaching it so that, as ever, the person designing the operating system can make a reasoned choice about how that's going to work. Okay, so we'll look at all these different options, and then you can think about the best way to do them. Why do we have to do memory management? Actually, it used to be that we didn't. Well, we did, but only to a certain extent. Early computers, you just loaded stuff into memory and ran it. And it was up to you not to overwrite the operating system or overwrite your own program. So if you think back to the LMC, there would be nothing stopping you in the LMC putting in some code that actually overwrote your own data or even overwrote your own code. Self-modifying code was actually a thing that people used to try and save some space. And I definitely wouldn't recommend doing that. But originally, when you had one computer, one person running one program, you could do whatever you wanted with it. And if you got it wrong, that was your problem. We've kind of moved on a wee bit, and we're now in a space where even if it's still single user, it's multi-program. In other words, we're running lots of different programs on one computer. So I don't want PowerPoint overwriting my Teams, or Firefox overwriting my File Explorer, or even worse, all of them overwriting my mouse pointer, which isn't working, or if it is, it's not doing anything. Goodness sake. So we have to have some way when we bring our programs in, because remember, all programs run from memory, not from disk. So we bring them in to memory. And we have to have some way that we can store all of these different things in memory, but protect them from each other and protect the operating system. So part of the operating system's job is to say, okay, you're in memory, you're running, but you've only got a certain amount of memory to use. The fancy name is base and limit. So every process that you bring into your memory has a base and a limit register commonly. There's other ways of doing it, that's a common approach. That simply says, okay, Word, you start at memory location 120900. You start at memory location 300040. Your size is 120900. So your limit is at 420940. In other words, you're not allowed to stray outside the space you have which is here. And in fact, if you ask to access any memory location that's outside there, if you ask to access one of these, or heaven forbid, one of the operating system ones, the answer will be no. So we put that into hardware. And part of the reason we put it into the hardware is because, not surprisingly, if you're doing this with every memory request, you want it to go as quickly as possible. You don't want every memory request to be slow. So every time the CPU requests a program location, it goes and it does a check, and it says, is it greater than the base? So is it greater than your base memory location? Is it less than the base plus the limit that you've given it? So you've given the process a certain amount of memory to use, in this case 120900. Is it less than the base plus the limit? In other words, does it fit into does it fit into this memory space here? And if either of those conditions is not fulfilled, it just says, no, we're going to trap this. We're going to say this process has tried to access some memory that doesn't belong to it. And we're going to flag an error and tell it to stop doing it and stop being so nasty as to try and access other processes' memory. So anybody now want to ask why we were watching a Disney ride?
Because just like it, each of those cars have their limits and they cannot exceed them, so it doesn't turn into one big bumper car ride.
Absolutely. So the cars could move a wee bit within their own lane, or in this case within its own memory space, but when it bumps to the edges, it stops it, doesn't let it go any further. So that's in hardware, and as I say, that ensures that the speed is kept up to date. But of course, all hardware that we have to put in is expensive. If you have to add in extra hardware to a computer, that costs money, but it's worth it to stop the systems overwriting each other. So let's remind ourselves what has to happen for anything to run. Normally, programs reside on external memory, commonly a hard disk. If you want to run that, you bring it into memory to start to run, because programs only run from memory. And again, go back to your LMC. I know it's an incredibly basic system, but it's exactly how every system works. You loaded up a program. You wrote a program, you put it into a text file, and you loaded it in. In the LMC, it got loaded into the post boxes, which are your memory locations. All computers do the same thing. There is one slight difference, though. Your LMC, as we were talking about, it's a single user, single process, so it assumes that it has the whole memory. So it loads it in starting at memory location 0. We don't have anything to worry about like an operating system or other processes running or anything else. We have one thing and one thing only. So it can be brought in at memory address 0. And when you start running the program, you start at address 0. You start at the beginning. But if you've got multiple processes running, you're going to have to start not running from 0. You're going to have to start running from wherever you have said your base is. So when you're creating your programs, you can't say go to memory location 123. What you have to say is go to memory location start of program plus 123. So you have something called a bind. All of these addresses can relocate. They are not fixed. They are from where you start plus. The example there, the process has been loaded into memory location 74,000, and if you want to access memory location 14 in your program, it translates to memory location 74,014. And there's a lot of different places that you can do, a lot of different ways that you can do that. You can do it at compile time, but that's going to be really hard. When you're creating a program to say, yeah, I know where this is going to run in memory every single time. Well, good luck. Perhaps if you're writing a system that is a dedicated system, so a real-time system, you'll know always what's going to be in memory because you have to ensure that the sort of things that happened with me there when I was starting my PowerPoint don't happen with your real-time system, because you don't want your ABS brakes slowing down because your media system is scanning your USB drive from MP3 files. You want to make sure that a real-time system runs in real time. So it might be at compile time, but that's unusual. It might be at load time. So when I load a new system into my Windows machine here, it says, okay, where have we got some space in memory? Oh yeah, we've got some space here. In this case, the blue bit is the space. I'm not sure that you can actually see that too well. Hang on, just... I'll just run even yet another program to slow the machine down. Okay, so this blue bit, when you load it in, it'll go, yeah, we've got some free space. It starts up at 880,000, so that's where you're going to be. So at compile time, that gets loaded in, and you take a note of where it is. And that's relocatable code. It doesn't matter it's going to 880,000 or 100,000 or 567,203 because you're using these relative addresses. And there's another option, of course, which is to run it at execution time. And that's clearly a whole order more complicated and suggests actually that we can split up not just each process, but that each process can be further split up into smaller bits. And we'll talk about how we'll do that later. In either case, we have an option. You don't need to remember this. Those of you that do programming will have an understanding of what this is doing. It's taking some code, it's compiling it, linking it in and putting it somewhere in memory. So we have this idea that there's two ways of addressing memory. There's a physical address space, what you actually have, the chips that exist. They don't change. But you've also got, as well as those physical addresses, logical addresses. Start of program plus 10, that kind of thing. So when you are running the system, the logical address for your program is translated into a physical address. And that opens up some other tantalizing possibilities. Your physical addresses, the amount of memory that you have stays the same. But what if your logical addresses were in essence unlimited? What if you could pretend that you had a system with 512 gigabytes of memory when in fact you only had 4 gigabytes? Perhaps one of the things we can do is have some way of taking our logical space, our logical memory space, and putting that into our physical addresses so that we can run more things than would actually fit in real life. Exactly the way I'm doing here. So we'll talk a bit more about that as well. I said earlier that when you're translating these things, it has to be fast. It has to happen really quickly because every instruction that you're processing requires one of these translations. So we have a hardware device called a memory management unit. It could be as simple as saying, give me the address you want and I'll add on a number. A relocation register. Yeah, I know you think you're starting at memory address 0, but I've slotted you in at memory address 12,000. So every time you ask for memory address 0, I'll give you 12,000. And every time you ask for memory address 1, I'll give you 12,001, and so on. That's actually quite helpful because whoever's creating the program doesn't have to think about physical addresses, they think about logical addresses, they think about their own program. And everyone who's creating the program can do that. They don't have to think about the wider system. That's down to the operating system to sort that out, as it should be. That's why we have the operating system. So as we run it, we set up our program in a logical address space bound to a physical address space. Something simple like this. CPU asks for an address, you add on a number, and you get a physical address in memory. The other suggestion for that is we don't actually have ever in memory. Why are we loading things that we're not using? So there's this, again, this idea of physical and logical space. Why would we load our table of contents generator for Word? Why would that be in memory all the time? How often do you use a table of contents generator? How often is that code executed? Perhaps what we can do is only load the code that we are using. Now, we've talked about this before. We've talked about this idea of code being localized. So in loops, you go round the same wee bit again and again and again, and you tend to stay in the same place. We talked about it when we were talking about caching, the idea that we can have a small bit of memory that will allow us to speed up everything that we are doing, because most programs stay in the same space and then move to a different space, and then we can update. So let's add that into the mix. Maybe one of the things that we can do is, counterintuitively, when we ask for a program to be loaded, let's not ask for the program to be loaded. Let's ask for the first bit of the program to be loaded. Let's only ask for the actual bit when we're going to use it. This actually was quite a common technique. When I programmed systems, I'm going to give away my age now. When I programmed systems in the 1980s, it was on a PC that had 64 megabytes of memory. The program that I was creating was 512 megabytes. So it was programmed by me in a series of blocks. So there was a kind of controlling block, which was about 6 meg, I think, from memory. And then I had a series of functional blocks that couldn't be any more than 20 megabytes. And that allowed space for data and operating systems and so on. So every time I wanted to do a new thing, I would manually take out the function that was running and bring in the new function. So programmers could do this if they have large amounts of code and only minimal resources. So again, this is still done in some specialized systems, but in general, we don't do this now because it requires the user to decide what's coming in and out. The operating system doesn't decide, whoever programs it decides. And as I say, for something like a real-time system or something like that, yes, you might want to do that. But in general, this doesn't happen too much these days. Instead, we want to get the operating system involved. We want to use that same idea, but have it happen automatically. That suggests that we can't link to things, and the term is called statically. So we've talked before about the operating system providing services, something as simple as an OK box. If our program wants to put up a box that says OK and have you click on it, you call some code, and the operating system provides that. But that code probably isn't located at memory location 1000 or 2000. It's located somewhere. It's in memory somewhere, and actually we don't care where. We don't want to know. So we tend not to use static linking, the idea that we know where something is and we call it, because that becomes tricky to manage. Instead, what we do is we call the API, call the stub, and that then locates it in memory. So that's called dynamic linking. All of these libraries are dynamically linked. They are dynamically linked libraries. They're only brought in when they're needed, and they're put into different places in memory. Does a dynamically linked library ring any bells for anybody? All gone back to sleep? Let me ask the question in a slightly different way. Has anyone ever seen a file on their Windows system called, with an extension of .dll?
Yeah.
All of those DLL files are dynamically linked libraries. They are functions that's available for your system, but they're not loaded unless they're required. And wherever they're loaded is entirely down to the operating system. We don't know where they're going to be. We just call them as they're needed and bring them in as they're needed. And of course, all of the systems, all the programs that we run use these shared systems. So my PowerPoint can have an OK button, my Teams can have an OK button. So it all uses these things. So they're shared. So one of the things the operating system has to do is to cope with knowing where these libraries are, cope with bringing them into memory on demand, cope with the programs not knowing where they are in memory, so it has to point to where the operating system has loaded them in. And if you want another fancy word, it has to make sure that the code is reentrant. In other words, it has to be able to be used by more than one other program. This is starting to get complicated. Okay, so we're now getting to the point where we're thinking that we have lots of things going on. We have this difference between physical memory and a logical memory space. This idea that we don't load things unless we need them. So let's think about the practicalities of how we might go about implementing that. Let's think about swapping. You've all come across swapping. You've all heard me moan about swapping. It's that time where you switch from one program to the other. Your system decides, oops, this isn't in memory. Actually, it's on my hard disk. So in order for me to run this other program, I have to swap out something to make space in memory, go to the hard disk, save it in there, and then go back to the hard disk and load in the bit that I want to use and bring it into memory. So that horrible time when you're working away at your computer and your hard disk light comes on and it stays red for a while, that's what's happening. There's swapping going on in the background when the amount of things that you're trying to run exceeds the physical memory. So it has to use its logical memory space. And the only place to put things that are in a logical memory space is on your primary storage, something like a hard disk. And again, those of you that are sitting at your Windows computer can go to the settings do a quick search for swap file, and you'll find that on your hard disk there's a file designated as a swap file, and that's what it's for. It's to augment memory and allow files to be transferred back and forth so that you can pretend that you're running all these things in memory. But as we've discussed before in terms of process scheduling, a lot of them don't do anything. They sit there. My Firefox has been sitting there since I started this PowerPoint presentation. It hasn't done anything. So it will have been swapped out to logical memory. When I first started this PowerPoint presentation, PowerPoint was running in the background because I'd queued it up ready to go. But it wasn't in memory because I hadn't done anything with it for 20 minutes or so. So part of the delay was probably the operating system going, okay, so I'm running Teams and I'm running Firefox and I'm running a file explorer, and actually I'm running multiple Teams programs because I've got Teams in the background and I've got a specific Teams meeting. So which do I swap out in order to bring in PowerPoint? And it takes what was in physical memory, puts it into the swap file to save it, and then goes back to the swap file to bring in PowerPoint. Normally it happens fairly seamlessly, it doesn't take too long, but once you start loading lots of programs onto your system like I've done here, once you have reasonably limited physical memory, it can cause a problem. So we swap memory all the time. We have a logical memory address in our swap file on the disk, and we bring it into our physical memory when we want to run it. And we take it out again when we've stopped running it. And that brings up yet another question. If you swap something out and then bring it back in, does it have to come back into the same place in memory? And if it doesn't, what do you have to do with all this stuff that you're doing in the background that suddenly, if you said it was loaded at 12,000, so you went to 12,000, 12,001, 12,002, what happens if that suddenly changes to 30,002, 30,003, 30,004? We're doing an awful lot in the background to allow us to do all these things. Some operating systems just go, no, forget it. So they do kind of actual swapping. So they'll swap one process for another. So you can have Teams in memory or you can have PowerPoint in memory, but never the twain shall meet. Others are slightly more sophisticated and do allow you to just bring things in, and then they will cope with them being in a different place. So we end up with something like this. We have processes in our backing store, so a hard disk or an SSD. When our main memory is full, we will swap out a process and swap in another process. So we just swap them back and forth. Operating system stays where it is to cope with all that, but we're just swapping processes in and out. So it's a fairly simplistic way of doing it. Yes, we're running lots of processes at once, but not really, because it's just when we switch to the other one, it swaps. So it's convenient, but not really much else. So when we want to do it, we have to save what we're doing to the hard disk, go back to the hard disk, bring in what we saved there before, and load that into memory. Not surprisingly, that's slow. Disks, even SSDs, are much, much slower than memory. So there's an example there for a specific hard disk, and I'll let you go through that calculation on your own. Trust me, it's correct. But what it suggests is that a 100 megabyte process might take 4 seconds to swap. In other words, 4 seconds between you going from one process to another, which, as you well know, feels like an eternity. That's assuming that you can immediately access the hard disk if there's not a process already saving a file or loading a file or putting a file into the print spooler. These things take lots of time. So we'll look at slightly more sophisticated versions. Mobile systems tend not to swap. They don't have much space to begin with. So what they do is they simply have one system running at a time. So you swap from one to the other things that aren't contained. And it asks, iOS simply says to other apps, look, I'm down in space here, I really need you to get rid of some memory. And the operating system will only jump in if it doesn't. Android is a bit more hardline. It'll just say to other applications, no, I need the space. You're dead, goodbye. It's not quite that nasty because it will save it. So it's similar to saving the state to hard disk, saving a process state, that kind of thing. It will save that. So that when you come back in, it can swap back in where it finished. All right, so we have all these things. They're all in memory. We've said that they may or may not come back into the same place, which brings up another question. Is the process contiguous? Have you come across the word contiguous before? Well, it's a simple yes or no. Maybe I should throw up a poll on it. Have you heard of the word contiguous? Just put a Y or an N into the comment. I don't care. Something so I know that you're out there. Contiguous just means that it's one after the other in memory. So say we have a process, so it's a single process, but it's got these different libraries in it. So that's library 1, library 2, library 3, library 4, all making up process 1. So these are all bumped up against each other in memory. They are contiguous. Do we have to do that? Can we have the same process, but say that library 1 is there, and library 2 is there, and library 3 is there? Do they have to bump up against each other in memory, or can we sort it so that they can be anywhere we want? So instead of this idea where you have the operating system and you have one huge contiguous user space for memory, maybe we can put things in different places. That would be interesting, because then that would also suggest that we can swap each of those libraries in and out and only bring them in when we want them. So we're back to this idea that we only bring in the table of contents library when we want it. And we don't have to reserve a huge space in memory so that that table of contents can fit seamlessly against the rest of the Word application. It can go wherever it wants in memory. So instead of just saying where we are, the CPU asks for an address. It checks that it's within its limits. Helps if I do it on your screen. It checks if it's within its limits. If it's not, same error as before. But then it adds on a relocation register. We're putting it somewhere else in memory. So we start having this idea that processes can move about and be anywhere. So here we're partway through a system. So that's processes 2, 5, and 8. Processes 0, 1, 3, 4, 6, and 7 have started and exited. They don't exist in memory anymore. Which brings up another question. If the process exits, like process 8 is doing right now, it's creating a big hole in memory, which is good because it means that we can load in a new process or even more than one process. But we may have holes in memory. And you can see that these processes are all different sizes. What if we wanted to reload process 8? Well, there's not a space big enough. Even at this point, there's no space big enough. What if we got rid of process 5? So process 9 is running, process 2 is running. We've now got lots of space. So we've got all this space here for process 5, all this space where the hole in memory is. That's easily big enough for process 8, but they're not contiguous. They're not contiguous in memory. So we can't load process 8, not unless we do some shuffling around. Maybe, what could we do? We could take all the processes and move them all to the start of memory and make the hole as big as possible. So we could start shuffling things about. What would be the downside of doing that?
Sorry, Tony, could you say that again?
If you got to the point where you have lots of holes in memory, if you add all the holes together, the space that you have in memory is big enough to load a process, but because the holes are all in different places in memory, they're not contiguous, you can't load that process. You could then move all the other processes that are in memory together to free up that space and put it all in one big space. But what would the downside of that be? What would it take to do that?
Time.
Time. So if you wanted to reshuffle all the processes that you have in memory and you wanted to move process 9 up to the start of memory here, you would have to go through each byte, transferring it from where it is to the start of memory, and then do the same for process 2 and move it up to shuffle in next to it. That would take time. So it's possible, but there are issues with it. There's another thing that we would have to think about as well. So again, we've got memory, we've got multiple holes in memory, and we want to run another process. Now, because we've got multiple holes in memory, it's possible actually that that process could fit in lots of spaces in memory. So there'll be holes big enough to accommodate that new process. Which hole in memory do we put it into? Do we just go through memory and chuck it into the first one that we see? Do we keep a list of the holes that are in memory? Look at the size of our process and say, okay, let's try and match it up. We've got all these holes, we know how big they are, let's try and get the smallest hole that we have to fit it in. Which means that the leftover hole will be small, so you don't waste too much memory. Of course, if it is small, then the only thing that will fit in that leftover space is a really small process. So maybe you do it the other way about. Maybe you put it into the largest hole that you have available, on the basis that that then leaves the biggest available space, which might be more suitable for more processes. All of these options are used in different operating systems and for those reasons. Which one is best, again, very much in inverted commas, is down to the operating system and what you're expecting it to do. If you analyze it, as it says on the screen there, worst fit is the worst also in terms of speed and storage utilization. So if you do the analysis, worst fit doesn't work as well. So this idea that we have memory, that we're slotting things into it, that we have to start then figuring out what spaces we have in memory, what processes we want to run, how we're going to fit those into those processes. These holes are called fragmentation, and you've probably heard about that in terms of disk management. So if you store a file on disk and then delete it, that space on disk becomes available. But as you use your disk, the stuff that you have stored becomes fragmented. It starts moving around the disk and you have holes. It's the same idea, but for memory. So we have fragmentation in memory, and there's two different types. External fragmentation, and just a reminder on class test day that these blue things are things that might come up. External fragmentation says we've got lots of holes in memory. If they were all together, we could fit in this process, but we can't because they are not together. They are not contiguous. Internal fragmentation is where we're using one of these allocation techniques. And we put our process into memory, but it doesn't quite fit, so there's stuff left over. We can actually, again, analyze systems and try to understand what happens. And it turns out, as you won't be surprised to hear, that whatever size of system that you have, in general, you waste half of what's left, because you've got a random size of process. So whatever you're wasting, sometimes you waste a wee bit, sometimes you waste a big bit, but on average you'll waste half of it. So that's a 50% rule. The suggestion I made that you could put all your blocks of memory into one place, that's called compaction. So you shuffle everything together, put it on one block, which means you're left with one big block of memory to use. But it takes time. You can't do anything else while you're doing it because you've got to use up all the I/O to move things around. As I say, it's exactly the same as the problem that you have running a disk. So what we want to do is think about ways of attacking that problem. But I think what we will do is take a quick break first. Does anyone have any questions before we take a quick break? Okay, in that case, have a quick comfort break and I'll see you in 10. Okay, and we are back. Everybody, it's time to get a cup of tea. I'll take silence as acquiescence. Okay, so let's finish off talking about memory, and let's take all of these concepts that we have been thinking about, and let's see if we can't bind them together and come up with an approach that might be helpful. So, how about we start thinking not of a program, but of bits of a program? So the sort of things I've been talking about so far. We don't think of Word, we think of a table of contents generator and a footnotes generator and a spell checker. If we think about our program like that, we can split up all these things, have them in different places, a function that calculates a square root, some data stored in the stack, the main program, and we can take those things and put them into memory wherever we want, at any space and at any place in memory. I should have made myself tea. At any place in memory that we want. There's nothing that says that it has to be contiguous or one after the other. Perhaps there's a way we can create a setup that allows that, and that's called segmentation. So we start thinking about a program not as being one-dimensional, starting at 0 and going to the end, but as two-dimensional, different bits, and where you are within that bit. And the fancy name for that is a tuple, where you have a segment number and an offset. So the segment is which one of these bits that you're running, and the offset is within that bit itself. Same kind of idea as with a full program. You have a base, where does it start? And you have a limit, where does it end? But you have to do that for all of them, not just for one, but for 4 and 2 and 3. So you have multiple pairs of base and limit. So again, fancy name for that is a segment table. So if you have a table that stores all the information about one particular program, that presumably starts somewhere and you need to point to the start of it. So you start having a segment table base register and a segment table length to get an idea of how many things are in that. So we start ending up with a whole bunch of things that we need to keep a record of, and also the calculation about whether the access to the program is legal starts becoming a wee bit more complicated. But for that, we start to free up how we approach memory. Instead of saying, no, we need all of this and we need it all at once, no matter what, we're saying, okay, well, let's just load in bits. Let's load in parts of the system and only load in the ones that we actually want when we want them. So it's more complicated, but it gives us more flexibility as well. And that's usually the trade-off. We do the same sort of protection things. So again, because we have these limits, we can still check to make sure that what we are trying to access is within the part that is owned by our system. So we've got another one of these diagrams. So again, the CPU is asking for, again, helps if I show it on your screen, the CPU is asking for some memory. There's two parts to it. There's the segment, segments. And there's the location within that segment. So as before, we make sure that it's within that segment. If it's not, we have an error. But we also have the segment going to our segment table to say, is that even our segment? And if the segment isn't, we have another error and we trap that as usual. But if it is, we find out where it is in memory. We find out the starting place and the ending place. We add those on to our offset that we've already checked, and that gives us our address in physical memory. So it starts getting more complicated, but is a lot more flexible. Is everyone happy with that? Because it's quite an important concept.
Yep.
Okay. Thank you. Okay, so we have programs. We split them up into segments, which are functional units, specific things that the program does, like functions for square roots or the main program or data. What if we extend that idea? What if we say, okay, well, let's take it away from what the program does. Let's not even concern ourselves with the functional parts of a program. Why don't we just think of the program as being a certain size, where we have the main program, we have the stack, we have the symbol table, we have functions, and we have the subroutines. And instead of splitting it up in functional chunks, why don't we just split it up and say, okay, let's just have 1K chunks. And we do that for every program. We have a 1K chunk. Now remember, one of the things that we can use is the idea that programs go around the same bit again and again. So quite often that 1K chunk is what we'll be executing at the time, and you won't need any of this other stuff. So in the same way as we only load in the segments that we want, perhaps if we divided it up into these chunks, we would only have to load those chunks that we need. Computing would be a lot more fun if they did call them chunks, but what they call them is pages. So we split up each program into pages. We split up logical memory into pages. We split up physical memory into pages. We decide how big each chunk is. So that's a frame, somewhere between 512 bytes and 16 megabytes. And again, that will be a choice for the operating system designer, depending on the kind of data that you're running through. If you're running through big, massive databases with all of the Bank of Scotland's customers in them, you probably want 16 megabytes. If you're running through my Excel spreadsheet of my friends, 512 bytes is more than big enough. So you decide how big you want these things to be. So if it's in physical memory, it's called a frame. If it's in logical memory, it's called a page. So you have a one-to-one relationship between the logical idea of you splitting up your program. They are then loaded physically. So you split up your logical memory into a page, and each page will then be slotted into a frame in physical memory. We need to ensure that we do a few things clearly. We need to keep track of things, not surprisingly. We need to keep track of how many frames we've used, what pages are in what frames. And of course, don't forget that our logical space, is quite significantly bigger than our physical space. We've split them up into the same sizes. And we start mapping them. We're running this part of the program just now. So that goes into physical memory, but it accesses some data that's down there. And that goes into physical memory. So we've got two parts to the program loaded into physical memory, not contiguous in memory, and all the other stuff is just ignored. We don't even have this physically in memory. These things are all in logical memory on hard disk. I'll let you think about that, and it's not because my door's knocking. Back in 2 seconds. I hate it when there's nobody else in the house. Okay, so we can start locating logical programs into physical memory. But we can do more than one, of course. We might have another logical program, still bigger than physical memory, but not as big as our other one. So we have L1, L2, and bits of that can also be sent to physical memory. That goes in there. And that goes in there. Now the nice thing about this is because we've set things up so that our pages and frames are all consistent sizes, we know that we can just take that chunk and put it in. We don't have to worry about fitting things in because they're all the same size. It also speeds things up because we're not loading and unloading full systems, nor are we loading or unloading even chunks of systems. So we're not loading and unloading these segments. We're loading and unloading a fixed amount of data, somewhere between 512 bytes and 16 megabytes, or actually whatever it is. So we have got all these things. We know how many frames we have. We have more physical, whatever much physical memory we have, we divide it up into those frames. And then all the programs that we're running, we divide up into pages, and then we just swap them in and out as and when they are needed. We keep track of it, so we have something called a page table. So that's this idea of knowing what belongs where. So we have a page table that keeps track of all this. So it has a frame and a page, and it just keeps track of numbers. Okay, so we have a page table going. We keep track of these fixed sized chunks, and we swap them in and out. Now, there is still internal fragmentation. So remember what we're talking about? We're talking about the idea that this last chunk here is unlikely to be the full size. So if we had a 1K chunk, that last bit might be, say, 800 bytes. So we're wasting 224 bytes. So that chunk won't fit in evenly. So we still have a wee bit of internal fragmentation, but that's part of the choice when you're setting up the page size. Trying to get that right between bringing in as much data as you can and not wasting too much. Okay, so we have a page number linked to the frame, and then to find out where we are, we can still do our same thing. We get our page number and then we add the offset. Where are we within that particular page? So again, one of our usual diagrams, the CPU this time gives a page number and a logical address within it. The page number gets sent off to our page table that figures out the physical frame that it's in. That frame then goes on and gets added to the offset, and that points then to the address in physical memory. Now again, because we're doing this for every single memory access, we want this to be in hardware because we want it to be fast. So we end up with something like this. Logical memory, multiple pages. We have a page table where we store each page. So the pages will just be in order, 0, 1, 2, 3. And then that will then point to the frame in memory. So page 0. And our page table says that's in frame 1. So we look over here and we see that frame 1 is page 0. Page 1, that's in frame 4. There we go, page 1, frame 4. Page 2, frame 3. And look at that, they're contiguous, but they're not in order. And that's fine, we don't care. And page 3 is in frame 7. Okay, so we can start to use that to figure out where things are. Then within it, we can start to figure out the specific parts so we can get our offset. We can start to work out some of the things in terms of fragmentation. So how big should the page size be to have the least amount of fragmentation? Here we've got a 2K page, we've got a process that's 72,766 bytes. So 2K into that gives you 35 2K pages plus 1,086 bytes left over. 1,086 takes up of 2,048 means that you've wasted 962 bytes, which out of a 72,766 byte process isn't too bad. It won't always be like that. Sometimes you'll waste a lot. Sometimes you'll waste hardly anything. Sometimes you'll waste nothing. In other words, the waste can go between 1 and page size -1. And on average, you waste half of it. So you waste half of 1 frame per process on average. And again, that's part of your calculation. And as we seem to be saying all the time, it's about finding a balance. If we're going to waste half a page on average each time, let's make the pages small. Let's have a 1K page or a 512 byte page, so that we only waste on average half of that. But we need to keep track of all these things. We need to have our page table in memory that says which page is in which frame. So the smaller we make our size, the larger that page table has to be, and we waste memory. So it's about finding that balance as usual. And every operating system has chosen its own balance based on the types of users it has, the types of programs that they run, the type of data that it processes. So the choice for a single user Windows PC is very different from a multi-user IBM mainframe for those reasons. However, it gives us lots and lots of positives. It means there's now as big a logical space as we want, because in theory, we can have every program that we run available to run all the time, because they're in logical space. And it's only when we actually start doing something with them are they brought into physical space. We don't worry about whether they're contiguous or not, because the page table allows us to see where they are in physical memory. And it doesn't matter if they're in front, behind, wherever, we don't care. We don't need to do so much working out because each size is the same. It's just the next chunk. So we don't need to worry about segmentation. We just slot it in to the next empty page in the page table. And we then keep that in memory. We need to point to it in memory because, again, we want that to be fast. We don't want that to be on a hard disk or something that we have to go and look up, because, of course, we're looking it up on every access. We're looking at that page table on every access. So we keep that in main memory. And we have a start of it, a page table base register and a page table length register, same as we had with the segments. That then means that every time we access a memory location, we have two memory accesses. One to access the page table to figure out where we are, and then one to get the actual data. In essence, we are we're doubling the time taken to access memory. I don't think I need to put up a poll to see whether that's a good thing or a bad thing. So what we do is we implement more hardware. And remember, this is more cost. If we implement hardware, that's a physical cost, and that has to be budgeted for. So again, it's this idea about, are we willing to accept that cost in order to implement these kinds of schemes? And that's the kind of choice that's made all the time. The hardware that we need is called associative memory, or translation look-aside buffer. In essence, it's cache memory. So instead of having the page table in main memory, you have a special bit of cache memory. Now remember from computing systems last year, cache memory is much faster than main memory. It's the second fastest access you can do outside of having a register. And in fact, quite often page tables now are stored on the CPU to be as close as possible. So you have associative memory implementing the page table in order to keep that as fast as possible. We also need to ensure that we understand which process is running in order to ensure that some processes don't access other memory. So we need to associate the process with the table as well. So we might have something called an address space identifier. In our translation look-aside buffer, in order to tell us who owns which bit. And in fact, some systems go even further. So they might say, right, well, we are going to implement this, but actually we're also going to have an operating system. We know the operating system always takes the first 50 meg of memory. So let's just say if you're accessing an operating system, don't even have that second one. Anything that starts from location 0 up to 50 megabytes, yeah, just go straight through. So we are choosing which ones to use. We're putting in lots of different hardware, lots of optimizations, all to try and get a fast access. Including this associative memory stuck on the CPU, which simply links up the page and the frame. Like every other cache, of course, the associative memory probably isn't as big as the page table. So we have a two-step system. So when the CPU asks for an address, this is a logical address that the program has asked for, it asks for it in two parts. It gives a page and an offset. That page is then checked against the associated frame number in the TLB. Translation look-aside buffer. That then gives us the appropriate frame that we add to the offset and gives us our physical address. As with cache, not every item in the page table is in the TLB. So if it's not in the TLB, if it's a TLB miss, we have to go to the page table and that brings it in and we finish the memory that way. A couple of things to note from that diagram. You'll notice that it asks the TLB and the page table at the same time. The idea being we don't want to wait and find out whether it's in the TLB or not. If it hits the TLB, fantastic. We've already asked for it. And if it don't get a hit, then we've already asked for it in the page table and it'll be coming in, albeit slowly. We've also missed out the part where we would have a feedback to say, okay, if we're going to keep looking for this page, we should probably put that into this TLB cache. so that the next time we ask for it, it is there. If we have that, then we can start working out access times, effective access times, because it's always going to be longer than just going straight to memory, because we're going to have to look up something, whether it's really fast TLB or not quite so fast main memory. So we're going to have an effective access time, which is longer than access time. But it depends on the size of your TLB. It depends on the size of your cache. Depending on the size of the cache, depends how often you'll get a hit in your TLB. And the more often you get a hit, the faster it is. The less often you get a hit, the slower it is. So that all gets added in. You work out the hit ratio. You work out how long it takes for a TLB search compared to a memory access search here. And then you can work out an effective access time like this. Again, don't worry about all the Greek characters. Trust me, this is how you do it. And you can start to then fiddle with your parameters.
Tony,
question.
Yeah. Is this going to be in the second test?
Well, it's in blue, so what do you think?
Yeah, that's what I'm saying.
Remember, I've already cut down these slides, so the stuff that's left in is the stuff that's in the test. But again, if you're happy with the chapter tests, you'll be happy with the class test. So spend time on the chapter tests, and you'll get a good feel for what the class test will look like. Yeah, so we can start to fiddle with the numbers. We can start to see what happens if we only have an 80% hit rate against a 99% hit rate. And that will depend on the size of our TLB and so on. What we want to do is try and get it as close as possible to our standard memory access time. And in this example, we've got an effective access rate of 101 nanoseconds. So in effect, we have slowed down our computer by 1%. But we've been given all these other things in exchange. There's other things that we have to do to make this work. We can decide whether or not we can read or write to a page. So we might be able to read, for example, the code that creates an OK box, but we're not able to write to it. So we need to have a bit that says whether it's read-only or whether we've got write access. We also need to decide whether it's valid or invalid. Is it actually part of the process or is it not? In other words, can this process validly access this memory? And if it can, as before, we say, no, you're not allowed to do it. So here we've got an example where we have multiple pages. Those pages, as usual, are mapped to a page table showing us where they exist in physical memory. So page 0 is mapped to page location 2, so it's valid. Page 1, 3, that's valid. Page 2, 4, that's there, that's valid. Page 3, 7, yep, that's there, that's valid. Page 6 doesn't exist for this process. So if anything asks for that, we know that there's a problem, it's invalid. So we don't even bother trying to link it somewhere. We just say, no, that's not valid for this one. So we've got read-write, we've got valid or invalid. We've also got that re-entrant thing that I was talking about, the idea that we can run code from more than one place. So we might have shared pages, pages that can be used by more than one process. So we also have to decide whether a page is shared or private. So these processes might have their own stuff, but also shared stuff. So it becomes more complicated, but we get an awful lot out of it for that. Any questions? I know you're all there because you had your cameras and your microphones on earlier, so I know that you exist. Okay, if there's no questions, let me stop the recording.